quite a bit of issues with weather and all that, but that's okay. That doesn't change the goals that we want to meet in this course. And I took advantage of the weather. I just sat down whole day and plotted this thing yesterday. So you can see what I do in my snowed in time. I'll just kind of tell you. I'm not going to post the mathematical solutions because I really want you to do it and be able to get to the final form of the band structure. But let me just say that for the semiconductors of high interest, such as silicon, germanium, gallium arsenide, diamond, they all have this FCC crystal structure, and the crystal structure has a cubic symmetry. This is kind of described in great detail in your in the slide notes that you have in the course. And just to be again, I mean, I'm going to try to summarize this aspect of it again. Silicon, gallium arsenide, and germanium. I mean, these diamond, these semiconductors have a crystal structure which looks something like this. So they have a cubic underlying framework. But for example, you may have a silicon. If it's silicon, let's look at gallium arsenide. It's a better example because there are two separate atoms in a basis, and I'm going to describe those later. So you have so the lattice sites. Now this is a crystal is equal to mathematically a set of points, which is the lattice, plus a basis. The basis has all the details of the atoms in it. And the lattice is completely unaware of what atoms they are sitting, whether it's gallium arsenide or silicon, germanium, diamond, it doesn't care. The lattice is actually exactly the same for all of them. So the lattice is just a set of points. And for these three-dimensional, simple cubic or diamond lattice, this is kind of called as a diamond crystal structure. The lattice happens to be the following set of points. It's for this is a face-centered cubic, or FCC, a face-centered cubic. So if I take the cube, the vertices are all part of the lattice. These are all lattice points, and in addition to them, the centers of each face is a lattice point. The center of the face is a lattice point. Center of that one, you can see, in a 3D geometry, it gets a little complicated. And the distance between two lattice points in this direction is not the smallest distance between two lattice points. This distance is what is called as the lattice constant, at least conventionally. You can call whatever you want to be the lattice constant. You can call this, you can call that, whichever you want. In silicon, in gallium arsenide and all that, typically this is what's called the lattice constant. And it's typically 5 point some angstrom, 5.3 angstrom, I forget exactly how much, something like that. Okay? So that's the distance between two lattice points like that. Okay? And if I kind of repeat these lattice points, you can see that I can have another cube, another cube, another cube, and some points are shared and so on. And you can fill up the whole space now, right? So that's real space, and in silicon or diamond and gallium arsenide, attached to each lattice point now, there's a basis of two atoms. So this is this is for the class of semiconductors. We're talking about silicon, gallium arsenide. For gallium arsenide, it is one gallium atom and one arsenic atom. So this dimer is what repeats in space. And the way it's oriented typically is if I draw a body-centered cube, a diagonal from one vertex to the opposite end, then so if that's A, what is the length of that thing? Right? It's the square root of 3 times A, right? That whole thing. And if you go along that direction, just 1/4 of that point is the so this is gallium, let's say, This is where a gallium atom might sit, and 1/4 of this is where the arsenic atom will sit. Let's shade the gallium atom as well. So this is the basis. And the basis could have gallium and arsenic, or it could have silicon and silicon, or germanium and germanium, or indium and phosphorus, indium phosphide. All these are different semiconductors. For all of them, the lattice is exactly the same, but the basis is different. Does that make sense? So these are the 3D semiconductor, typical 3D cubic semiconductor crystals. So now why am I dividing it up into these 2 points, lattice and basis? Because now I can take this dimer and I take this and translate it to this point. This is my second lattice point. Okay? And then I'll have a gallium here, and exactly at the same angle, at this, there'll be an arsenic there. Then I translate it here, there'll be a gallium here, and then arsenic sticking to that. So this thing just repeats. And by repeating this, you will be able to form the whole crystal of gallium arsenide or silicon. Does that make sense? That's the difference between lattice and basis. And I think, so the chemical bond is between here and here. So this is gallium, arsenic, gallium, and then you form these tetrahedral bonds now. So there's another one at the center. So this is the chemical bonding is between gallium and arsenic, not between gallium and gallium. So for example, here, right? If you have an elemental semiconductor, germanium or silicon, then all of them are the same, right? Except you can't get away from the fact that it still has a 2-atom basis. Both atoms are the same. So that's the right? So that's the difference here. And there's one problem where you have to kind of make this distinction in your assignment between the lattice and the basis, and you'll realize that even in that simple picture, you must have a 2-atom basis, because otherwise you won't be able to, repeat your lattice points. Now, the unit vector, the vectors that join the, again, let's forget about the atoms for a second, the basis. All the geometry of this problem is determined by the real space lattice vectors. Big R is, let's call it M1 times A1 plus M2 times A2 plus M3 times A3. These are the real space lattice vectors. The reciprocal space lattice vectors are, let's call it N1 times B1 plus N2 times B2 plus N3 times B3, right? We've talked about those. Again, these are completely unaware of what atoms you put in. They don't care at all. Right? They only care about the lattice points. Right? So therefore, the real space lattice vectors and the reciprocal are kind of identical, except for some length differences for silicon, for diamond, for germanium, for gallium arsenide. They're all the same. So because the lattice points are the same for all of them. And what are these 3 vectors, A1, A2, A3? So you go from this point, for example, you go to the first phase center, that's 1. Choose that to be A1. Go to the second phase center, A2, and the third phase center is over there, A3. And you see, you form if you join these points, you form a kind of a tetrahedral shape. Okay? And this is the smallest repeating unit in this whole picture. So if you take this sort of a pyramidal shape and you turn it, and move it and translate it, you will be able to fill the whole space. So this is called the Wigner-side cell, or the real space analog of the Brillouin zone in K space. So the smallest repeating unit in real space. It's not the whole cube, as you can see. You can do much better. It's much smaller than that. The whole cube still works. You can repeat the whole cube, but there are a lot of redundancies there. There are shared things and all that. But within this volume, there's only 1 gallium and 1 arsenic, and that's it. It contains the basis as well. Right? And then that repeats. So the arsenic, or the second atom of the basis, sits right at the centroid of this, thing, of this object. It sits at the centroid. Okay, so now if you know A1, A2, so if this is the lattice constant, let's fix this to be the origin, and let's, for example, call it X, Y, and Z, right? Then maybe you can tell me what is A1. I can write it down by looking at it now, right? So A1 is, which one did I even write? I messed up here. Okay. That one, right?
Yes.
Okay, let's call that A1. So what would that be?
1/2, 0, 1/2.
Right, so let's see, X you're going half, right? Z, Y you are not going anywhere, and Z half, right? So 1/2, 0, and 1/2. But then what's the length of that vector? A, right? A is the length, right? So that's your A1. And A2, A3, you can see the 0 will move around, right? Right? And from here, A2 and A3, I leave that to you. You can find out your B1. How will I find B1 now? What is my reciprocal lattice vector? I want to go from real space to lattice. Right? So this is 2 pi times A2 cross A3 over the triple product cross A3. Right? And you can evaluate it, and you will get something here. Right? So this quantity here is the volume of this little thing, and it's like A cubed by 4, or forget, something like that. You can evaluate it completely. Okay? So that will be B1, and B2 and B3 you can evaluate all those things, and then you get all your reciprocal lattice points as well now. Right? So now when you look at the reciprocal lattice points, I'm going to say that, for example, what you can do here is, I'm going to magnify it a little bit. So here's what I'm doing. I mean, I'm doing exactly what I told you. A1, A2, A3, right? These are the vectors, real space lattice vectors. Then I find B1, B2, B3, just cross product over, triple product, right? So it just calculates all that stuff. And in general, my reciprocal space G vector is some integer times B1 plus integer. Right? So I get all reciprocal lattice points right away from here. And obviously, I also get all real space lattice points also from there. Right? And now you can construct your K-space picture. And in K-space, again, this is a 3D picture. So let's say you have Kx, Ky, and Kz. All we have done here is found a set of points. We haven't found anything detailed of band structure, just a set of points in K-space. Right? That is effectively what you call is the Fourier transform of the lattice points in real space. That's what it is. So yeah, so basically the center of that is always called the gamma point. This is a notation from group theory. We don't have to worry about all the details, and that's when Kx, Ky, Kz all are 0. And that's obviously an allowed vector because all these three, n1, n2, and n3 are allowed to be 0. They're all integers, positive, negative, and 0. Right? So that's that point in the reciprocal space. And then you can see you can go B1, B2, B3, and all that. You can move around now. Right? And you will see that there is one point which is out here, which is at 2 pi over A times 0, 1, 0. You'll see that point. And there'll be, by symmetry, there'll be one here. It's cubic symmetry, so there'll be one there. I mean, there. So you'll have all these points in K space. These are just points, just no shape yet. And okay, so when I take these points and I say now, just to be very clear, why are we going to the K space? Because I know that if I had a free electron in this periodic crystal, I mean, obviously there are atoms sitting in the way, then the energies of the free electron would be given by h squared by twice free electron mass times k plus g whole square. That's the nature of, because of the Bloch theorem, you get this g now, right? Again, where does it come from? If you had a completely free electron, there would be no g, right? Just h squared k squared by 2m. But because now you have a periodic potential and you have scattering, basically it mixes up states of k plus g, k minus g, all kinds of things. It mixes up those states, right? So your wave functions look like e to the power I k x. In free electron, it becomes e to the power I k plus minus g, right? Right? That it kicks, and that when I kind of go and say that, let's say I'm not going to, I know that the atoms are in place, but I'm not going to consider their potential. I'm going to turn the potential off, but have the symmetry of the lattice still there. So that's called the nearly free electron model, in which case your Hamiltonian, your potential turns to 0, and your Hamiltonian again goes back to h squared, del square by twice mass, and this del will pull out these k plus minus g's, and it'll drop it here, and that's your energy. So does that make sense? I mean, it's just kind of the nearly free electron model, which says that I still have free electrons, but the wave functions now satisfy the symmetry of the lattice. So that's different. That's not a case of a completely free electron. A completely free electron, there is no lattice. So that's a slight difference. And now what I'm going to ask, the question is, for every point in K space, by the way, these are special points in K space. These are the G, where the G vectors are, right? But all these Ks inside are still allowed, right? What is the spacing between 2 points here? These are allowed points, by the way. What is the spacing? It's 2 pi by L, L along the y direction. These are all allowed points. Right? But these points, which are the reciprocal lattice vectors, are very special points, around. And we'll see they're also very high symmetry points. And at each K now, at each K, let's say, here's that K. At each K, there are multiple energies now. Because I can take G is equal to 0, I get one energy, right? Take G is equal to 2 pi by A times 1, 0, 0, I get something else. So these are the different bands now. Right? Does that make sense? I mean, that's the nearly free electron model. At each point now, I can have different energies. If the electron was occupying this K space point, then it can have multiple energies. And those multiple energies are basically by just, turning around, sweeping through the values of N1, N2, N3 from 0, 0, 0 to 1, 0, 0, minus 1, 0, all that stuff. You get different energies, right? And so when you take those and you make a plot of them, that's what you get. So this is what you get. So essentially, that's what I'm doing. I'm plotting this whole thing now, just saying, here's my free electron energy, It's just what I told, it's this quantity, right? Because I already found my reciprocal lattice vectors, big G's. I can write my energy as K minus G, or you can do plus G, it really doesn't matter, mod squared, and that's what we're doing here, right? And the G now depends on these integers, which are the indices of N1, N2, N3, and you can just change them now and plot different bands. Does that make sense, what we're doing here? So now there are some points in the space here. Thank you, I think, is that hopefully better now, yeah. There are some points in the K space which have very high symmetry, and then those are, let me just bring that up. So the center, as I mentioned, is gamma, okay? And then as I start moving out, let's move along, one of the 1, 0, 0 axis. So this is 1, 0, 0. This is 0, 1, 0. They're all equivalent in cubic phase, right? I mean, it's just we are labeling it. The crystal doesn't care what you label it. But physically something is similar if it goes this way or that way or that way, right? It's cubic symmetry. So therefore, this is, as I move along here, this should be KZ. I think I just pulled it up from Wikipedia yesterday. So, so this is the gamma to X point. And as you go from gamma to X, if it was a free electron, its energy will increase. It will start from K is equal to 0 to, it will become a parabola, and that's what's happening here, gamma to X. It's just plotting, right? The curvature is that of the free electron, right? But for that curve is only for G is equal to what? 0, right? When N1, so G is 2 pi by A, let's say, and call it N1, comma, N2, comma, N3. If I put all three 0, then I get that curve. Right? And I put maybe N is equal to 1, then I will get something else now, right? And then N is equal to 2 or minus 1, and you get all those things on top, right? So that's from gamma to X as the electron moves in. Is that clear?
Say that again.
Yeah. So as if the electron starts moving in this direction, it starts from K is equal to 0, and it starts moving along the X direction. So along the X direction, let me write this term out, because along the X direction, K, I'm going to use K minus G, let's say, K minus G whole squared. So energy is proportional to, I'm just absorbing this h squared by mass and all that, okay? So K along the X direction is just Kx, right? Minus N1 times Gx, right? Does that make sense? Gx and whole squared plus Ky is actually 0 along that direction, because this is there's no Ky or Kz, it's just Kx here, minus actually let write down the k is kx, comma 0, comma 0, and this is n1.
So this is just for the special case, though, of
Yeah.
gamma to x. When you go from any other point to any other point, you have to pick the direction between the points.
Correct, absolutely. So any general direction, you can assume kx, ky, kz, right? And you can assume a g vector like that, take the difference, take absolute square, and plot it. Does that make sense? I mean, that's what we're really doing. But whenever, so, and in general, it's 3 dimensions, so the electron could be moving in any direction, right? But the band structure, whenever you see a band structure plotted, it's always plotted along directions of high symmetry. Meaning, you can see that this axis has a very high symmetry because I rotate this way, they're all the same, right? Whereas if I were going from here along a curve like that, that would have no symmetry, right? So these are high symmetry points, gamma to k, it has rotational symmetry, it has translation, and that sort of thing, right? Reflection symmetries. So that's why it is plotted along that direction. But in general, the energy, for every k point, there's a set of band of energies, and you can plot all of them. All of them have the same formula, it's just this. Does that make sense? Okay. This is an important point. So this is just the nearly free electron model. And now if you go from gamma to L is along the 1, 1, 1 direction. Therefore, all 3, this, and this would be the same. Kx, ky, kz would be the same, right, along that direction. Right? Does that make sense? So and so on. And now, by the way, n1, n2, n3 are whatever you choose. 0, 0, 0, 1, 1, 1, whatever you choose. For different values of this triplet of integers, you get different bands. But this one depends on which direction you're moving in, right? And yeah, question?
Are these letters like gamma, L, X, K, are those standard? Like they can be found tabulated somewhere, or are they different for every crystal?
Oh no, these are standard. So gamma would always stand for 0, 0, 0 point in K space. And L, it's a standard point. When we say in silicon that electron was moving along the gamma L direction, we mean it's moving in the 1, 1, 1 direction. If you say it's moving in the X, gamma X, we know it's 1, 0, 0. And in fact, in silicon, it makes a big difference whether it goes that way or this way. But they're standard.
But are they always just directions, or is X a point?
X is a point in the K space, and the direction would be, say, gamma to X is a direction, or so what are the directions we are plotting here? Gamma to L, gamma to X, gamma to K. Again, there's no reason for it to plot it this way. You can plot it that way, but typically in books, this is how it's plotted, so I just put it this way. You can also move from X to X to U. You don't have to start from gamma. You can electron can be moving here. That's a very high energy electron. Typically, you won't reach that situation in a semiconductor, but in a metal you may. So you can move here. You can kind of go around in various contours and come back to where you started, and that's really what. So this is the handout. Again, I'll put this up too. This is also in your notes. But if you look at what I've noted down here is these are different EK diagrams. And then you just kind of join them, X with X, gamma, gamma. Now, K and U happen to be actually group theory states that they are the same, though they might look different here, K and U, but you can notice they're in the middle of the hexagons, this hexagonal facet, so actually they're the same. It's very weird, it's a contorted thing, so if you fold them, it'll assume a shape that you can't draw anymore, right? So you kind of join all of them, and here's the band structure now for the nearly free electron. This is a nearly free electron model. And what I've noted here are the degeneracies, meaning this is only for G is equal to 0. There's only one G vector, one combination of N1, N2, N3 that leads to this band here. And similarly for this band. Right? But if I go up here, maybe this one, there are two G vectors that lead to this exact same band here. If I go up for this one, there are 4 G vectors. So these are the degeneracies. These are all allowed. These are all allowed. So in other words, this band at this state, there are 4 energy states, and each of them has spin of 2. So there can be 8 electrons that will fit into that state there. Does that make sense? The degeneracy meaning the bands are falling on top of each other. They belong to different G vectors now. And with this sort of idea, you can go around the whole crystal, and if you know that your electron is moving along a certain direction, you can find out what energies are allowed for it, and so on. Now, if you go to the next page here, which is now that's all well and good. I know that many of you are, some of you are having hard time plotting it, and it's not trivial. At least for me, it took quite a bit of time to kind of plot all of them together in one shot. But if you can get them separately, that's okay. Gamma to X, gamma to L, that's okay, just fine. And I know that it can be done in a better way, but you can kind of make this plot. And I just want to make sure that everybody is on the same page, that this is just the plot of the free electron band structure, but with these G vectors moving things around and throwing up more bands. That's all there is to it. So yeah.
So for each of these curves, how do you label what that curve, which G corresponds to which curve? I'm still confused with the...
Right, so that you choose, So when you, for example, let me give you an example. I'm plotting energy of free electron, gamma to L, that's my notation. And I'm plotting three, x-axis, y-axis, kx, ky, kz. And then here's my G vector, -1, -1, -1, n1, n2, n3, all three are. Here's another G vector, -1, -1, 0. So I just kind of run through them.
Each curve has its own associated G vector.
Absolutely, yeah. Each curve has its own associated G vector. And some of these curves have like 4 G vectors. They all lead to the same curve. So that's a degeneracy. Yeah, yeah.
Can you go back to where you were a second ago?
You mean up here?
No, sorry, to your slides.
Yeah.
Are each of those numbers a different G vector?
You mean this one?
Yeah.
So here, this is the degeneracy, meaning there are 4 different G vectors which lead to the same EK curve. There are 4 different. Maybe this 1, 0, 0 this is definitely not 1, 0. It's probably 0, 1, 1, 0, -1, -1. I mean, all of them lead to the same, same EK diagram. So that's the degeneracy of a curve. And you can see this actually a very simple thing. All we have done is we were saying there's a free electron model, but the wave function satisfies the symmetry of the crystal. The crystal lattice is built into this now. And that's why you have all these kind of strange features. Because in the free electron model, all you have is a parabola. That's all there is, right? But because now the electron will get scattered, and scattered as in the electron will interfere with the crystal, and it will experience the periodicity of the lattice, you have multiple bands now formed, here. And it picks up the momentum of the crystal, or rather momentum of the, it picks up the periodicity of the crystal through this, addition or subtraction of G vectors now, as the electron moves through the crystal. Now, yeah.
So when any 1, 2, 3 are all 0, that's the bottom point band parabola where you had 1.
This one, yeah. The lowest one are when all are 0.
You have it's scattering back in and back off the gamma point. Was that manually done, or was that part of the calculation?
Which one? You mean this one?
So if you follow from the gamma in the bottom, and
yeah,
you follow that trajectory up right and then bounce off left.
Yeah. So this one is actually, let me just say, so between gamma and X, I'm plotting the energy dispersion for one G vector this way. This is for another G vector.
Okay.
And this is for another G vector, and I try 4 G vectors, they all give me this. And so that means the degeneracy is 4. And so these are, all you are doing is changing N1, N2, N3, all right? And you're generating these different curves now within the same window of energy.
Okay.
Within the same case, K energy, yeah.
What does it physically mean
Yeah.
when all of these points are like meeting back on gamma? Like at higher energy, you have a lot of points meeting on gamma.
Yeah, I will discuss that now. So this is actually a very interesting question, because now you can see that there is electron energy. So this space here, this x-axis here, is what we are calling as small k. Maybe I'll go to that side now. All right, let's use this as our x-axis. So if you had a free electron, then you know that it can have, the free electron wave function is e to the power ikx, and you can find its momentum by applying the momentum operator on a free electron, right? And the momentum of a free electron is just h bar times k, right? That's the momentum. That's de Broglie relation. That's one of the first things we started out with in this course, right? But here, in a crystal, the k has a very different meaning. And then let me just make sure that we are on the same page here, right? The K, actually, how about this? Let me just move that. Let me finish a bit more discussion, and I'll come to that in a few minutes today. Okay? The K here is what's called the crystal momentum. It's not the complete momentum of the electron, and we'll just talk about that briefly. Okay? But before we go there, let's look at the next page here, which is by the way, before I go next page, any more questions? I would like to address this first because this is a very important thing, and I wish I want to make sure everybody gets what's here. You know. This is a free electron model, but it has the symmetry of the lattice built into it now. You know, right? And how you generate it is what I mentioned. In Mathematica, if you're using Mathematica or MATLAB, one of the nice things you could do is define these high symmetry points, you know, like gamma point and X point and K point and all that business. And then you can define your axis. If you're going from gamma to X, you can just say that, you know, these are vectors, you know, from origin. So again, I mean, this is just a detail. I know that there are many ways to do it, and you don't have to stick to this way of doing it. But so gamma point. So let's say I want to go from, you know, gamma to X. I just, you know, this is actually trivial. I say I start at gamma, and then I define some sort of a variable plus X minus gamma. You know, so that's a vector, right? It just, you know, the direction just starts out with this factor eta to be 0, and then you tune it to 1, and you end up there. You know. Does that make sense? So that's just kind of defining the line, you know, in K space. If you want to go from K to U, maybe something like that, you know, that's a trickier situation. You can see how do you write that line, right? But if you are dealing with vectors, it's very easy. Or say X to U, you want to go along that line, X to U, for that slice of the band structure. So then you have to find out what is my Kx, Ky, and Kz along that line, right? Before you can plug in here. And to do that, what you, again, if you have written down your K point and the U point and the X point here in 3D space, it's very simple, right? You take the difference of the two vectors, and you start out from one point, X point, and you go to the other point. You know, this sets up your Kx, Ky, Kz very easily. You know. And then you can just say, plot the whole thing now for me, and it plots it. You know, so if you look at why are we spending so much time on this, the next thing we want to look at is, so that's a nearly free electron model, but what happens once you put atoms, you know, and the potential in its way, right? And actually, the very weird answer is not much changes. You know, here's the nearly free electron model that, you know, we just talked about with no atoms in the way. And here's the full band structure of germanium. Now you put in all this stuff into it, you know, atoms, the atomic potential, and all those details now. And you can track through most of it, and you will see that most of it remains kind of similar, most of it. I mean, obviously there are some changes, otherwise, you know, all crystals would be exactly the same, right? But you can see that, you know, the bands gamma to X, you know, this one, and you see that there was a degeneracy here, these two were meeting, and this is split because of the crystal potential now. And you go here, this is not split, it stays. And you go up, and you can now track. Yeah, you know, one of the questions I think you were asking is, what is the significance? Why are there, you know, what happens when so many of them meet here, right? So one of the things that happens is when you turn on the crystal potential, depending upon the symmetry of the potential and you know and which G vector that band comes from, it will split or it will not split. Depends on that. Here it splits it. For example, that place for germanium, it splits it there. And it happens to be a very important point for germanium because this is the band gap of germanium. This is the gap of germanium. It splits around that point. And as you go on to higher bands, you can see that, you know, there are, for example, this band kind of almost stays, you know, up there. It is, you can see the tail of that. And then there's a, you know, crossing up there, it splits. Some bands are heavily deformed. You know, for example, this band here, you can see. That's heavily deformed. It splits, you know, multiple times and all that. But what I wanted to say was, for the most part, you know, for the most part, the bands remain like nearly free electrons. It's not changing much. It's only when you reach these points of high symmetry, gamma point, X point, all that, that's when most of the violence happens and it opens gaps and all that. And that's why these are the Brillouin zone points. Remember, this is the G vectors in K space. And the electrons get interfered the most when their wavelength matches up with the crystal lattice wavelength, right? And that's why you have all this violence, opening and all that happening around those points. Now, so this is called the empirical pseudopotential method of calculating band structure. It's a little more involved, but not too much more involved than what you are doing in your assignments, which is the LCAO or the tight binding model. The tight binding model is essentially taking the two silicon atoms in the real space or the two germanium atoms and looking at the energy for on-site, energy for hopping, and then translates it by this vector, by that vector, and by that vector. Right? It translates it, there are four nearest neighbors in any. So, for example, this atom has bonding to this one, that one, and that one. It's the center of a tetrahedron. It's bonded to four of them, and then so those are the four nearest neighbors. Electron sitting at one side can hop to four nearest neighbors, and so those are the hopping elements. And each point in the lattice now in the tight binding comes with an s orbital, then a px orbital, py orbital, and a pz orbital. It comes with four. Right? There are two atoms in the basis, four orbitals, and therefore 2 times 4, 8. So you get an 8 by 8 tight binding Hamiltonian. And you solve this thing. These are all the hopping elements, N1, N2, and N3, and then for our nearest neighbor terms. Okay, so I'm not going to kind of go through too much detail. You are working on it. And I know there may be some mathematical difficulties in plotting it, but let's do, I want all of you to kind of have this done once, and make it work. And another thing I mentioned was for each orbital, there will be a band. That's just like you start off with an orbital and you collect and then form a band. So if I start with 8 orbitals, 2 atoms and 4 orbitals each, right? S and 3 p's, S and 3 p's. So 8 orbitals, meaning I'll end up with 8 bands. Right? So that's yeah. There was a question here.
Yeah. So on those large 8 by 8 matrices,
yeah.
How do you solve this in Mathematica? Because Mathematica, this would run for hours and hours.
I see. So if you
We're just taking the eigenvalues of it, right?
Yeah, for this problem, or you can find eigenfunctions too. But yeah, here we are doing eigenvalues. Now, if you make sure that it's it is Hermitian, meaning it's complex conjugates. Generally, it should calculate. Let me just say, on my computer, it takes like 15 seconds or less for an 8 by 8. So typically, if it's getting stuck, there's something missing somewhere, and it's probably trying to find imaginary, having a problem with that. So if it's set up right, though, if you set it up right, and you say find eigenvalues of this 8 by 8, it will give you the eigenvalues very it's reasonably fast because it's an 8 by 8 matrix. Now, if you're getting some error messages, typically, it's hard to decode from Mathematica, but let me just say that if you make sure that every term here is complex conjugate of that, then it should give you, and you can test it. You can first test it, say all my k's are 0, turn off all the k's, because you have to give it as a function of k, right? And as a function of k, as I start from 0, if I start with 8 bands, so I get 1, 2, 3, 4, 5, 6 here. It's 6, but they are degenerate. I think 2 of them are degenerate here, so there are 8 bands. You should get these energies right away. Right? And then what you're doing when you're plotting it is you are varying your k vector, moving it along that x direction or L direction, and then finding these 8 eigenvalues and just kind of stringing them together and plotting it that way. Right? So if you turn off your k, actually you can see it here. If k's are 0, this is 4, right? E to the power 1, e to the power zeros are all 1s. This is 4, that's 0, that's 0, that's 0. So you can see your matrix becomes somewhat simpler, and you can calculate the eigenvalues. Even actually, if you look at it, you can calculate by hand, but you can confirm whether Mathematica is doing it or not, because you just test it and then work. So if you have problems, still come by our email, and we'll take care of that. We'll let you know what might be the issue. But generally, this 8 by 8 should be doable pretty fast in Mathematica. Or MATLAB, or any of these tools that you use. Yeah. Okay, so and you can see in the tight binding model, you kind of capture most of it, but tight binding, in the nearly free electron model, you can continue as many bands as you want on top. In the tight binding, you started with 8, so you will be, if you started with 8 orbitals, you will get only 8 bands, right? And so you're missing out some stuff that happens on the top, at the high energies here. If you want to include them, you also include higher orbitals, instead of 2p or include 3p or 4p orbitals and 4s orbitals. Now in semiconductors, most of those higher states would be empty most of the time because your Fermi level in a semiconductor undoped is kind of here. So the very high bands typically don't get a chance to be occupied because you run out of electrons in most semiconductors here. But in metals, in some metals, you actually have quite a bit more. So you have this interesting Fermi surfaces, etc., and so on. Okay, okay, so that's the. I also give you. By the way, you can play with this if you want to be more familiar with the Brillouin zone of most. Of this diamond crystal structure. You can make your own model for the Brillouin zone and you will know exactly where are all these points. It's kind of nice exercise. But this is a very interesting table for tight binding models. Those of you may be interested in saying that, well, this is a silicon. I'm interested in a more crazier crystal, like maybe a perovskite crystal or a cuprate superconductor or something like that, right? I want to find out, because you see tight binding model is extremely interesting model because it tells you that once you define the crystal structure, the direction of bonds and the nearest neighbors, all these are fixed. N1, N2, N3, these are fixed, right? Now, all that you need to feed into this model is to calculate a band structure of any crystal, be it metal, be it semiconductor, be it topological stuff, whatever be it. What you need is what is the on-site energy if the electron is sitting on that atom. And second is how much energy lowering does it get if it hops to the next atom, right? From one orbital here to another orbital there. So here we had sp or pp orbitals, s to p, and so on. So this table gives you the on-site energies of all atoms, of interest in the periodic table. So that's what we call a solid-state table element. So here we had needed, if you want to do for gallium arsenide, you need the on-site energy of gallium. And you need the on-site energy for s orbital for arsenic, on-site energy of p orbital in gallium, on-site energy of p orbital in arsenic, right? So on. So this gives you the on-site energies of all elements. Let's say you had a cuprate, copper and oxide. It gives you the on-site energy of copper, maybe d orbital. And so you can choose those elements and then you create your matrix based on the crystal structure, and the numbers that go into it, the hopping elements and the on-site energies are all listed here. So this is kind of interesting because you can use it to get a rough idea of what will be the band structure of any crystal that you may ask, be it graphene or boron nitride or a complex perovskite crystal or anything like that. Obviously, if you have more and more atoms in the unit cell, the size of the matrix may grow and bigger, but the idea remains the same. Yep.
Can you explain what this notation means in the true bands? So the gamma 2,5 prime.
Yeah. I will, let's not discuss that. I think it's not necessary for this course, but these are group theory notations, and they are indicative of, four-fold rotation around some axis or something like that. It's not meaning if you sit there and you rotate it by, so 90 degrees will always listen. So it's a four-fold rotation. So some of these are just related to those things, and we don't. You can look deeper into it if you're interested, but I'm not going to cover too much of that in this course.
Do the L's correspond to the energies?
The L's?
On the left.
You mean L?
Yeah.
L's. Well, they definitely do correspond to these points where the bands cross the L. Where the bands cross, yeah. Right, okay. Right. So I'm just saying that these are the tight binding constants that go into the matrices for all kinds of crystals that you may need. Also, a word of caution: tight binding model has also got some limitations. It gives you the basic idea very fast, but if you want to push it, say, oh, I now want to exactly calculate my electrical conductivity, or I exactly want to calculate my band gap, that's not extremely accurate because after all it's also a model, and it has some approximations in it. But it gives you a fair idea of what should be the general band structure and the general conductivity or optical properties of a material. It gives you that very fast, and that's why it's very useful. And the other thing is it's kind of intuitive, and because you can think of electrons sitting here and hopping. I mean, that's all you need to consider when you calculate the tight binding band structure. Okay, yeah.
So you just said tight binding is somewhat limited. Is there sort of a key assumption in there? If I recall, there's one just saying you're only dealing with nearest neighbors, and the other that all the orbitals or orbital states were orthogonal.
Yeah.
Is it one of those two that's sort of the key?
Right. Let me just say the tight binding method by itself, by including next nearest neighbors, including more and more orbitals, in the limit of infinitely next nearest neighbors and infinitely large number of orbitals is exact.
Okay.
So the question is, in operation, when you apply it, how many orbitals are you going to retain? How many neighbors are you going to consider when you hop? That's where the approximations come in. The exact shape of the wave function and all that. So that's where. But in reality, this method is exact, right? If you kind of ramp up the size of the orbital, number of orbitals and all that. So, yeah. Okay, so now all said and done, what I will move on to now is after we have done all this, started with nearly free electron model, and then in this course I'm not asking you to do the empirical pseudopotential method. By the way, if you have done a tight binding, this is trivial too. This is called the EPM. It's a little more accurate band structure, and these days people use density functional theory and a little which is a little more involved. And so on to get to the true bands. But I just want to kind of make sure that all of us are on the same page that I'm actually pretty close even with my free electron model without the lattice potential. Okay? When I just turn on the lattice potential, I get gaps and all that, and that you're doing in this course. And I'm not asking you to do this, but it's no harder than a tight binding model. Let me just put it that way. Okay? So you can calculate that, and then you get your EK diagram of a semiconductor. And or a metal or whichever, and that's what we are kind of seeing here. And I'm just kind of this is also from your slides. I've just highlighted a few things of 3 semiconductors, and it's very much restricted. We are not looking at the whole K space at all. We are only going from gamma to X and gamma to L, gamma to X and gamma to L. So just to be gamma to X is the 1, 0, 0 direction in K space, and that's the 1, 1, 1 direction in K space, and we are looking at 3 bands, 3 semiconductors, silicon, germanium, and gallium arsenide. These are 3. All of them have the same simple cubic, diamond structure like this. Right? All of them, all 3 of them. Right. But now let's just kind of look at a couple of details before we go and answer quite a few of the earlier questions of what is the meaning of this K, and because what I want to do now is take this as an example of any semiconductor, and then calculate 2 things from this picture today. One is, if I have this semiconductor, how many electrons am I going to measure at a given temperature, in the semiconductor, or how many holes am I going to measure? I can answer that, and where will the Fermi level be? I can also answer that. And the second is, if I apply an electric field on a material of this nature with a known band structure, what will be the current in the material? I can also answer that, with all the machinery we have developed till now. So, okay, so just a couple of details. In silicon, if you count the number of electrons, remember there were degeneracies and all that. Maybe this was 2-fold degenerate, that was 1-fold degenerate and all that. And we know in silicon, the basis is 2 atoms, right? And each atom came in with 4 electrons, 1 s and 3 p's, 4 plus 4. So you have 8 electrons in the basis, right, of this. Obviously, there are a lot more electrons, but most of them have much lower, energies that are down here. These are core levels. They are not even participating in chemical bonding. The electrons from there cannot hop to the next side. They're stuck in the same atom, right? And we are not considering them at all. We are only considering the 4 outermost shell electrons, 4 from here and 4 from the next. And so we have 8 electrons. And when you start filling up those 8 electrons, I want to Okay, so just say that, if you start filling up from the bottom and you climb up, let me just make sure. So this is germanium, but actually similar. One of these bands has a two-fold degeneracy, two-fold bands are on top of each other. So I have 8 electrons to fill these bands. 4 from here, 4 from there, 8 electrons. So I start filling them. Right? This band, just look at gamma to x, actually. This is, how many electrons will be able to fit into this band? 2, right? So if there are n atoms, then n times 8 n electrons, right? N atoms in the whole crystal. Sorry, n, n, just get it. N of those Wigner-side cells, right? Big N, right? Then each cell has 8 electrons, so I have 8 n electrons in the whole crystal. If it could be a 8-inch wafer that we use, and you can calculate exactly how many electrons will be participating in this whole business, right? So now this band will take up 2n electrons, like this. This will take up 2n more, and now this will take up 4n because the degeneracy is 2, right? And so we have 2 plus 2 plus 4. I'm out of 8n electrons, done, right? And now I see that there's a gap. Okay? And so that's my valence band, top of the valence band, and that's my bottom of the conduction band. Makes sense? I mean, so that's for any cubic crystal, including gallium arsenide, indium phosphide, indium arsenide, germanium, all of them, same business, right? You run out of electrons right here, and this is filled band, filled band, filled band, empty bands, empty bands, empty bands, right? So these are the conduction bands of silicon, of germanium, of gallium arsenide. These are the valence bands of silicon, germanium, gallium arsenide. Right? The top of the valence band, you can see, is obviously curving upwards, and top of the valence band of all these semiconductors are at gamma point, which is at k is equal to 0, 0, 0. Right? Yeah.
Is this with type binding, or is this the actual bands? Or?
This is the actual bands. Yeah. It has a bit more work in it here. These are the actual bands, and these have been measured because of the importance of these semiconductors. These have been measured to great accuracy, and I'll mention also later you can measure these states by electrical methods, by optical methods. You can translate, and measure them. So, but the band structure, obviously experimentally there is some band structure, right? And theoretically, forever we are going to try to make it better and better, right? I mean, so because the experiment is what we know is experimental band structure is very close to this. That's all we know right now, right? Because one of the interesting things about experiments is you can never turn off any physics. Even the physics that we haven't discovered yet, it's still there, right? So when we do an experiment. So anyway, so the valence band top here, these are filled states, and the conduction band bottom are the empty states. What I want to kind of emphasize is for a large part of the remaining part of this class, we are going to only mostly focus on these circle regions. We're not going to look very deep into what happens out there or very high up there. And most of the electronic, photonic, thermoelectric, solar cell applications are based on these little pockets of K-space. Most of them, all the device applications take advantage of these little regions. Only when you hit the semiconductor with a very high energy photon, like an X-ray or something like that, then you kind of probe the deeper lying levels. But otherwise, if you apply a few volts across a semiconductor or shine visible light on it, you will not be really messing with all these deep states at all. So we have gone through a lot of work to get to this point, but we are going to now throw away all the details, but just understand that these are the important points in K-space. Now the lowest energy of the conduction band minus the highest energy of the valence band is the band gap of the semiconductor. It doesn't have to be at the same point in K-space. Right? Now in some semiconductors they are at the same point, gallium arsenide. The lowest point in conduction band here, state, is at the same point as the top of the valence band. And this is very special. This is called a direct band gap semiconductor. I think you probably may have heard of it. And these are extremely optically active. So they can absorb light very efficiently. They can emit light very efficiently. So most of the communication lasers today are based on InGaAs and gallium arsenide based materials. LEDs, gallium nitride, they all are direct band gap. And the reason for that, and we'll look at this in greater detail later, is because if you have a small, no mismatch in K for this and this state, an electron, if it were put here and this state was empty, it can transition to this state and it emits a photon, which is a light wave. And the photon has very little momentum. Photon is basically the energy. So because the photon is massless, right, it has very, very low momentum. And therefore, if you try to make this thing emit light, it cannot, because it is a very hard time doing it, because electron will go from here to there, and that has a very high momentum. That's not the momentum of light. It cannot. So this momentum mismatch is what causes direct bandgap semiconductors to be extremely efficient optical absorbers, emitters, and show very strong optical activity. Whereas indirect bandgap so this would be indirect bandgap semiconductor when the minimum of conduction band and maximum valence band are offset in K. They're not at the same point in K space. So, for example, for germanium, this is along gamma to L, along the gamma to L, which is kind of along the 111 direction here, right? Somewhere out there in K, and is very close to the edge. So maybe you can tell me how many such points are there in real K space, the whole K space. If I look at the minimum here, how many such points will I have? In the first Brillouin zone, that I mean. So 1, 1, 1, right? So there are 8 such points, right, in K space. Does it make sense? Because you can have each of them +1 or -1. So I can have one here, one the opposite side there. So there are 8 such pockets in K space where the electrons will accumulate for germanium. And in your class slides, let me just move over to that point. Where was that? I'll just, roll over. There are lots of slides here. Okay, no, I jumped over there. So there's one point where it shows the whole, K space. Okay, maybe that one. Yeah, you can see, this is essentially showing all the L points, so 8 of them. In the first Brillouin, now silicon, this is germanium, and it has the minima along the L valley, near the L valley, or L point in K space. Silicon is along the X direction, you see 100. The minima in conduction band reaches along the X direction. So how many should I have? 6, right? So there'll be 6 along the 100. So there'll be a little pocket here, little pocket there, little pocket, and these are oriented in this way too. So this is where all the electrons in silicon are going to sit in the conduction band. If they're generated. Yeah, there was a question.
No, you answered it.
Okay, yeah. And what about gallium arsenide? How many minima? Just one. It's at gamma point. It has no more degeneracy. You are sitting here. There's only one such point, right? So it has a. So therefore, this valley degeneracy of silicon is 6 for the conduction band, right? This is the valley degeneracy. That's what we mean. It's a valley in the energy space, the minimum, and so there's 6 of them. Valley degeneracy of germanium actually is 8, but it turns out that it's kind of shared between the next, half of it lies inside 1, and it's actually 4. But gallium arsenide and silicon should be clear that they are, gallium arsenide is 1. And this is what? Yeah.
So when we say valley degeneracy, the valley in the conduction band minimum has a degeneracy of 6.
Yeah.
But in the valence band maximum,
yeah,
is not also 6 necessarily, or in that case, at 8, right?
You mean this one?
Yeah. What is the degeneracy at that point? I mean, I can see I have a few bands meeting there.
Ah, okay. Yeah. Right. Okay. So this degeneracy, you can see, has come from geometry, right? Meaning because there are so many points in K space. Now, if you're sitting at the gamma point, the valley degeneracy of this point is how many bands there are, right? I mean, so if you have multiple bands here, this little splitting we're not going to discuss too much in this course is due to spin-orbit coupling. If you turn off spin, I mean, in reality you can't, but let's say in the calculation you turn off spin, then these will merge, and you have 3 valence bands one is light hole, the other is called heavy hole, the other is called a split off band. So there are three, valley degeneracy is 3. Let me just, I can't call it a valley degeneracy because there's only one valley, right? But there are 3 bands, so the degeneracy is 3. And that's the degeneracy that I had mentioned earlier here, these are the degeneracies that I had mentioned. I mean, how many bands are there, For example, at this point, 6, because they're meeting, 3 and 3 are meeting, right? And so on. So that's also a degeneracy, but that's not what I would call a valley degeneracy. It's just a band degeneracy, yeah.
So you still only have one valley degeneracy at that point.
Correct.
Because it's a gamma point.
Because it's a gamma point, there's only one.
But
Right?
you get degeneracy from the band.
From the band overlaps, yeah, that's right.
So maybe getting to the question I want to ask is when we say the valley degeneracy is 6 for this crystal, we mean the conduction band.
Only the conduction band.
We have to
Absolutely.
specify 2 valley degeneracies, one for conduction and one for valence.
No question, absolutely. Conduction band valley degeneracy is equal to 6. Valence band valley degeneracy is equal to 1 for silicon. Right. So that's right. So it's so each valley. I mean, this is upside down, but each valley you can determine its degeneracy. Yeah. And then from here you can kind of look at your K space and say, if I were in, if for some semiconductor or some crazy material, my minima was at K point, you can now find out how many degeneracies it will have and all that stuff, because they repeat. Yeah.
Can you explain one more time why the conduction band valley degeneracy for silicon is 6?
Okay, so right, so let's see. When you do all this band structure calculation for silicon, the minimum of this. So this is filled now, valence band, okay? And that's my conduction band, and the minima occurs in K space. As I'm moving here, it occurs. This is the X point, gamma to X. And the minima occurs somewhere kind of around here. That's where the valley occurs. But then if I reflect it, there's another valley here because there are 6 equivalent 1, 0, 0 points in K space. This, that, and that. So you can, another way to look at it is, everything that happens in this direction also happens along one bar, which is minus 1, 0, 0, which is along that direction. It happens along 0, 1, 0. 0, 1 bar 0 and 0, 0, 1 and 0, 0, 1 bar. So there are 6. And so there, yeah, okay. Now we look at this as a question and say that let's say I take this sort of, either, let's look at gallium arsenide. Let's say I take this gallium arsenide crystal and it's completely pure, pristine, no chemical doping, it's perfect, and it's sitting at room temperature. And these bands are supposed to be filled and these are supposed to be empty, right? Let's say sitting at room temperature, I can ask 2 questions. One is, one of the questions I can ask is how many electrons are there in this crystal, mobile electrons. Obviously, I know how many electrons there are because, I have 8 n electrons in the bands and you have more which are not involved. But how many electrons can actually contribute to conductivity and all that? If I measure electrical transport, how many electrons will contribute to it? So that we can answer now. And the second question is about this transport problem, which is the K. What is the physical meaning of K? We're going to answer these both. First things first, can you say, if I take this material and electrons are filled here and it's at 0 Kelvin, absolute 0 Kelvin, then this band is completely filled, right? This is completely filled. And we have talked about this earlier, but I'll also discuss this more as we move along in this course, that a filled band carries no net current. It carries internal currents, but no net current, because for each velocity, by the way, this is a very good example. I say that if I have a state here moving at a certain velocity, there must be a state there also moving with exact opposite velocity, right? But you see there's not in this picture. What went wrong here? Right? Yeah, exactly. So this is, be careful the way it's plotted. This is not the same, if you plotted 1 bar, 0, 0, then it will be a mirror reflection, right? So there will always be opposite. But because it's plotted along a different orientation at 90 degrees, it doesn't need to be the same. But if you plot 1 bar, 1 bar, 1 bar, then it will be a reflection on this side, right? So they will cancel, right? So the fill band is not conducting current, and so at 0 Kelvin then this will be all occupied, and that would be all empty, and there will be no net free carriers to move around. But if I take it to room temperature, you can see that at room temperature there is a finite probability that some electrons here. What do I mean by room temperature? Meaning the crystal of gallium arsenide is sitting on something, and that thing is at 300 Kelvin, right? What does that mean? That means that the crystal atoms of gallium arsenide are vibrating with a certain amount of frequency and all that. They're phonons, and that's what we mean by temperature, right? And if the crystals are vibrating and atoms are vibrating, the electron can pick up some energy from those vibrations, and it can pick up on an average kT of energy and can jump over there. Now kT may be much smaller than Eg, but it can still go because there can be this finite probability. Therefore, once electrons go from here to there, now I have some filled states of here and I have some empty states there, right? I've opened up conduction in this band because now it's not full. I've opened up conduction in that band because now it has some states too. So now I have some n, which is electrons, and some holes, p, n and p now, because of a finite temperature, right? We're going to do this mathematical details in the next class on Tuesday. And that will tell you exactly where is your Fermi level and all that stuff. We're going to look at that in the next class. But for the rest of the time today, let me answer this question of the physical meaning of the k in these pictures. What is this x-axis k physically? So this k is comes from actually the block function. So remember, for free electrons, the wave function is very straightforward. It's e to the power I kx over square root of L, right? This is free electrons. No periodic crystal, none of that. And when you have that wave function, you can find your momentum operator on that, and you get that's h bar k times psi. So and that's the momentum of the electron. H bar k is the real momentum of that electron, right? But now what we have done in the last few weeks is said that I want to consider the situation when the electron is seeing a periodic crystal. In which case, what happens to the wave function? What functional form does it take? It becomes a block function now. It's not a free electron wave function anymore. It's a block wave. So the wave function became a block function. And so now we write that as mostly like a free electron still, right? Except there is another part to it, u small k of x. And this thing is periodic with the lattice. Right? This thing is periodic with the lattice, meaning, we index it typically by k here. The block function looks like this, meaning if I forget this periodic part, this is still a free electron. You can see e to the power kx, right? But now there's the crystal modulates that function by this much, right? Periodically. Right? So if I take mod psi squared, it's periodic with the lattice constant because this is periodic, right? So uk of x plus a is equal to uk of x. Right. So when you take mod squares in the electron, and you can imagine, there is no reason why an electron, even in quantum mechanics, if you put it in a periodic potential, why it should be piled up in some place and not the other. It should be periodic, right? By symmetry itself, right? So as a result, now this is your wave function, and now when you apply the momentum operator on this, you will see that h bar k is not the momentum of that electron. It's not. Right? It has some extra stuff that comes from here. Right? It has g vectors and all that stuff mixed into it, right? So h bar k in this scenario, when you have a block electron, h bar times k is not the physical momentum of the electron, but it has another meaning, and that's called the crystal momentum, and that's just a name, but let me explain it. Okay? Crystal momentum. So that's what we are talking about when I say h bar times k, where k is now as part of the Brillouin zone. Let's say you have a bands like that and bands like that, right? Ek. Now this k we are talking about here, if I take that k and say I have an electron here, and so what's its momentum? Now its crystal momentum is plain. It's h bar k. That's the crystal momentum, and that's just a name. But what I want to emphasize is that's not the full physical momentum of the electron. The physical momentum of electron has many other components. It has some from G and minus G and all that stuff, right? It's mixed in, right? But its crystal momentum is h bar times k. Once you have a block electron, h bar times k is the crystal momentum. Now, physically, what does that mean? How do I differentiate between it? Now, the only thing that makes h bar k not the physical momentum is the fact that it's in a periodic crystal, right? It's in a periodic crystal. But the fact that it's in a periodic crystal has been accounted for in calculating your band structure. It's completely accounted for, right? That's how you got the band structure in the first place, right? Right? So in other words, so if I look at, this k, now that k came from perhaps, this band that was translated. So it's actually like k plus g or k minus g and all that, right? Came from different points like that. And when I apply an external electric field or external magnetic field to the crystal, to the electrons, then the equation of motion for the electron now in this band is given not by the total momentum, but by the crystal momentum. I mean, this is actually a rather very remarkable result, but it's a very important point. If I apply an external field on it, or in other words, let's say I apply a force on this electron state, right? How does the electron k change? That's always given by h bar dk by dt. Now this was true for a free electron with k being the real, h bar k being the real momentum of the electron. Does that make sense? But in a crystal, this still holds, and this is actually very remarkable. You can prove it, and I'm not going to try to even prove it. In a crystal, this still holds as long as we understand that this is the crystal momentum. Crystal momentum. And this is an external force. External force. What does that mean? What is the internal force? Internal force is the force of all the atoms and the periodic potential and all that stuff. That has already been taken into account and has given you this picture. It's all buried inside there. Whereas this is an external force, meaning if I apply an electric field times Q or magnetic field externally, then this is how what we track here is how the crystal momentum changes, not the real momentum anymore. Does that make sense? This is actually a very important point, and I'm just stating it at this, today we are out of time, but in the next class we'll see where it leads us, because it really makes all the effort you put into calculating the band structure worthwhile, because you can completely forget now that the electron is experiencing a periodic potential, because all that information is buried inside here. All you need to do is track the crystal momentum and don't need to worry about anything else. And then you'll get your current, you'll get your heat conduction, energy transport, optical properties, all that stuff from the crystal momentum. You don't have to worry about the internal momentum anymore. Okay, so I know that this sometimes is a confusing concept, but we will apply it a couple of times to make sure that we understand it completely. Okay, so the difference between the crystal momentum and the actual physical momentum of the electron. Okay, all right. And office hours 5 to 6:30, same deal today. Oh yeah, and the homeworks are due tomorrow. By 5 p.m. as usual. Yeah.